Video compression is another technique or another area which requires a lot of work. What happens with video is we are storing many frames, and so this needs more compression than images. So video is nothing but a sequence of still images that the eye perceives as continuous motion, and so these uh, frames are to be individually compressed. Now that is one technique, but that will waste an enormous opportunity. The opportunity lies that here is that there are many frames which are very similar to each other, and so we can achieve video compression in other ways also. Now the first, so redundancy in case of video compression, of if it is spatial redundancy, we can uh, create correlation between neighboring pixels. If it is temporal, we can understand what are the static regions which are repeating, and if it is statistical or coding redundancy, whatever are the non-uniform symbol probabilities, these can be given in the final stream. And psychovisual, as in eye is less sensitive to color detail, but it is more sensitive to brightness detail. We should keep this idea in mind. So the first idea is we should convert RGB to YCBCR model. Y stands for luminance, which is the overall brightness, and CB and CBCR stands for the chrominance, which is the color information. Now here we will convert from RGB to YCBCR because human vision is more sensitive to brightness than to color detail. And so here, if there is any kind of loss, it's not visible to the human eye. That is, with CBCR, if I try to make some kind of change, it is not visible to the human eye. So there is a 4 to 0 scheme. Consider if I have 2 cross 2 Y samples, I will store only one CB and one CR samples instead of keeping all 4 CBCR values. That is, I'm basically reducing, if I have to store 4 here, 4 here, 4 here, so I'm reducing um, the CB and CR values. Instead of 4, I'm storing it to 1. So quarter, I'm reducing 4 values to 1. So quarter, that is, I'm bringing it to a quarter. And overall data reduction, if I see, 12 bytes would have been needed. Now here only 6 bytes are needed, 4 plus 2. So it is 50% overall data reduction. There is the concept of macro blocks and motion estimation. Now, macro blocks are nothing but dividing the frame into small fixed size tiles and then analyzing if these macro blocks are very much similar to the next frame's macro blocks. Instead of comparing my image at every pixel level, I can check at macro block level. Consider at macro block level, I check that there is a car, and so I'm seeing the transition for that car. So instead of storing the car and the car is moving by some 2 pixels, and after 2 seconds it is moving by another 10 pixels, instead of storing that entire frame information, I can just store car separately as macro blocks and then show by how much x value has it moved. So I can, for each macro block, the encoder, that is within, let's say within 10 further frames, it will try to look for the same matching frame for the best matching region. If it finds that within 10 frames that such a car region all it exists, that is indicated by the motion estimation. That is, it is indicated by how many pixels has it moved to the left or to the right or to the up and down. So for, let's say one portion of the car, I will check in 10 consecutive frames, is it available anywhere? If it is available anywhere, by how many pixels has it moved? So consider if this is the car. Here we can see that this is frame 1. So I will check for this macro block in the next 10 frames, where has it moved to. So like this. And so what I will do is, now I need not store pixel by pixel information. I should only store that this macro block after 2 frames will appear onto this pixel position. This is called as motion vector. First of all, I estimate the motion and I store it in a vector form, and that is motion vector. Now there is also motion compensation that is being done. So I will get the motion vector. Now once I calculate the motion vector, consider if my previous block is 100, 102, 101 and 103, and I predict my block to be same. That is, I am considering that it is totally matching, but the actual block there has been slight changes. It is 100, 103, 101 and 104, and so the residual or the difference between the previous block and the actual block is coming up to be 0, 1 and 0, 1. So now this is the residual is nothing but the prediction error, that is the pixel by pixel difference between the actual block and the block predicted by shifting the reference frame region according to the motion vector. So now here I will check the residual. Now, so a good motion match will leave very small residual or something that's zero, and this residual compresses far more efficiently than the original pixel value. And then there is the next step is transform coding or the discrete cosine transform. Now this will convert from the spatial domain into the frequency domain. Because it converts into the frequency domain, I will come to know which are the regions which are smooth slowly changing regions and which are the regions which are rapidly changing regions. So now I'm changing from the spatial domain to the frequency domain to understand the sharpness, the edges and the smooth regions in the image. So after I calculate that DCT, I will get more information in the low frequency coefficient. So let's say this is the original block. After applying DCT, I will get something like this. And here many of the values might become zero. The next step is quantization and entropy encoding. So now quantization means each DCT coefficient is now divided by a step size and it is then rounded off. So like let's say if I divide everything by 10 and round it off. So now all those values are further becoming smaller, but sometimes there might be a loss of information in this quantization step. Then after that I'm performing entropy encoding, and now entropy encoding as in uh, that is whatever quantized coefficient that I get plus the motion vectors, now they are compressed. Now they can be compressed using RLE plus Huffman coding or other methods that are there. Now once I do all this, I will get a group of pictures. Now group of pictures are nothing but different kinds of frames. There are three types of frames in I, P and B. I is nothing but the independent frame. Consider it like the first image that is to appear. Predictive, like a standalone JPG, it has no reference to any other frames. For this I cannot perform too much of compression. The next one is predictive frame. Now predictive frame is something which is possible from a previous frame. From a previous I or pre-frame, I can calculate this. So this is like a motion compensated prediction. Let's say the car has moved ahead by 4 pixels. Then there is a bidirectional frame. Now bidirectional frame is a frame in between. Consider if a car has to move 20 steps in 20 seconds, then I know that at the 10th second it would have moved 10 steps. So here what happens is I can construct the past frames and the future frames as well. For this I can, for these two kinds of frames, more compression is possible. So this is group of pictures where I have series of frames. There is independent frame at the beginning always. It will always begin with an I frame. That is a clean reference point. And then after that, the B frames always need a future frame. So the encoder must reorder frames internally. And so here a B frame cannot be at the end, and an I frame cannot, anything should always begin with an I frame only. Ending can be with an I frame or a P frame. So this is the pipeline. Initially, motion vectors are calculated, and then after that, residuals are calculated. To the residuals, DCT is applied, quantization zigzag plus RLE is applied, entropy encoder is done, that bit stream is getting passed. After that, the process happens in the reverse order. Inverse quantizer, inverse DCT, residuals are computed, and then depending upon that predicted frame, and then I'm getting the reconstructed frame. So like this, there is the the video compression, it is being passed as bit stream, and then finally at the receiver's end also it is being reconstructed back. There are MPEG-1 and MPEG-2 video standards. Uh, Usually MPEG-1 is a lower standard when compared to MPEG-2. You can go through the so here nearly it require this is 1.5 Mbps speed, and it usually stores information in the ratio of 352 into 240. It is VHS level visual quality, and this is not a very advanced MPEG-1 standard. This is like the video CD or the earlier digital video transmission methods. MPEG-2 standards provides us 15 plus Mbps. It stores information in the form of 920 into 1080 frame size, and it follows both progressive and interlace scanning. And this chroma subsampling, it is 420 for MPEG-1, but for MPEG-2 follows 422 or and 444 also.